Hey, so I really like this conference because it's nice and small. You know, it's kind of neat that as a small conference, you up here and basically go ahead and give some material that's kind of, say this is half-baked material. No, it's not half-baked material. This is material that I've been thinking about for a good long period of time. I haven't really presented it. I figured it'd be a decent place to go and try this out and sort of go and share with you some of the things I've been thinking about in this particular area. Does anybody notice that people are talking about functional programming more these days? Yeah, right. Why are people talking about functional programming more these days? Because Microsoft released C#. That's one immediate reason. Another one?
The 60s was cool.
The 60s was cool, right? Hardware, yeah, there's the whole thing of multi-core and all this other stuff too. I mean, you can look back and try to identify a particular reason why we're looking at functional programming these days. Partially, I think some of it, in a way, is kind of like a little bit of faddishness. Right? It's kind of like this notion that, well, you know, it's kind of like this is something, even though it's old, it's new again. And it's something that we ought to go and explore and deal with and stuff along those lines. My own particular path to this, though, is kind of interesting. Back in about 2001 or so, the Pragmatic Programmers, anybody ever hear of Andy Hunt and Dave Thomas? Right? They wrote the Pragmatic Programmer book and stuff like that. And one of the things that they mentioned is that you can gain an awful lot by going and choosing to go and pick a language every year and choose to just learn it, you know, and basically see what it does to your perception of how to program. And one of the languages that they chose one year, very early in the 2000s, was Haskell, okay, which is a very interesting functional programming language. It is kind of like Smalltalk is to OO, Haskell is to functional programming. It basically takes a couple of key ideas and carries them to the extreme. I thought, this is great because it'll take me completely out of my element, so I'll be able to learn more about programming, right? And I just found it so difficult that I gave up back in 2001 or so. But the thing is that I discovered a little bit later, kind of digging through it, that it was really a critical way of looking at things. And I started to notice this very interesting synergy between what I was doing in my day-to-day job and functional programming. Okay? The synergy is not really apparent until you kind of get deeper and deeper into it. As Adam mentioned, I wrote this book about working with legacy code. I spend most of my time now going around to teams around the world and helping them with very horrible, cryptic, crazy code bases, right? And it always seems that the hardest thing that you have to deal with when you're working in a terrible code base is that you want to go and change one little thing, but you're scared to pieces that changing that one little thing is going to go and have all these crazy side effects all throughout the system, right? And it turns out that in functional programming, there's a bit of an answer to that problem, right? It's kind of like, in essence, in functional programming, there's a strong emphasis on having immutable data structures, data that you cannot mutate. Okay? Now that may seem like a very strange idea, because how do you actually ever get anything done? But we'll talk about that a little bit more going on. It turns out that they have answers to some of these things. Another thing that happens in Haskell, which basically I wish we had in other languages, is that there's only one particular area in your program where you can do I/O, right? It's something called the I/O monad. Within this particular construct, you can do I/O. Every other place in your program, you can't call into I/O code, right? And for those of you who've worked with large code bases and tried to get things under test, I'm sure you've been aware of that situation where it's like, you know, you don't know how far down the call stack you're going to have to go before you arrive at something that's going to go and talk to a database or do something like this. And so you'll have to go and mock in order to go and get, you know, good test cases for the stuff you're working on, right? So many of these things are things that they were old, they're becoming new again. Like anything else, though, we're getting into this very odd period where people are trying to go and keep one foot, you know, in the river and take the other foot and kind of step outside of it, right? Right now, we're seeing that basically many functional ideas are being added to conventional OO languages. Two of the most apparent areas for this right now are Scala and F#. Right? They're both hybrid FP-OO languages, and they both allow you to go and create objects and functions and mix them and do all sorts of various interesting things. And a lot of the traditional mainstream languages are doing things like adding lambdas and stuff along those lines. But it makes me kind of wonder where we're going to go now, right? Because as soon as you have these two sets of features within a language, you start going and reaching this particular point of decision. You have to go and ask yourself, well, gee, you know, should I adopt a functional style in this particular area of my code, or should I adopt an OO style in this particular area of my code, right? Now, I'm not going to claim to know the answers to this particular thing, right? But I do have lots of thoughts about this and some things I think might be reasonable guidance until we sort of, as an industry, start to go and gain our footing in this particular area. I do have a fear about it because I lived through the days when people sort of transitioned from procedural programming to object orientation, right? And in that time period, believe it or not, but there were some people who wrote OO programs in a very procedural style. Okay. Is that far-fetched? Does anyone believe me? Okay. It still happens, right? Okay. But the fact of the matter is, it took a long time for the OO way of thinking to basically arrive within the community. And you start to see these things which were essentially C programs, ported into C++, and like, let's put a class around this big thing. And now we've got an OO program, and then just start marching forward and marching forward and marching forward. Turns out though, right, in functional programming and in object orientation, I feel that the impedance mismatch between these two paradigms is far more severe than the impedance mismatch between procedural and OO programming, right? Which means that we are going to go and probably say this, but in the industry, I think we're going to kind of screw up mixing these two things for a good while until we go and get it right. Okay, so I'm trying to go and sort of jump ahead and figure out, what can we kind of do to go and ameliorate this problem before it's really a problem. That's how it works. So we'll see what happens. First off, though, what is functional programming? Okay, it's extremely hard to talk about this now because really it isn't just one thing. It's an amalgamation of many different things in computer science. This is the definition that Wikipedia gives. Okay, and it seems to kind of cover the core of it in a sense. This is the thing which is very scary to people. We're going to basically see programs as mathematical functions now, okay, when we're doing functional programming. The other thing, too, is we try to avoid state and mutable data in our applications. And it's really very odd for us because in our typical day-to-day programming and object orientation, it's kind of like, state is our bread and butter. It's the thing we deal with all day long. We basically work with state. We assume objects to be stateful. We assume we're going to mutate state when we send commands to them, all these other things. So in the very beginning, it's almost impossible to look at this definition and go and imagine how you would actually structure programs in a functional manner. Okay? Here, the definition goes and contrasts it to imperative programming. You know what imperative means in this case? It's like you tell the machine to do something, right? You say, hey, I want you to do this. I want you to go and perform this function for me, this sort of thing, right? What's funny is that when you're working functional programming, quite often what you're doing is you're doing the opposite. You're saying, instead of saying, look, do this thing and change the state of the world and all this other stuff, you're starting to ask questions. You say, look, I'm giving you this data, give me a result back. It goes and gives me the answer to what I go and need to deal with. So it is a bit of an impedance mismatch, as I mentioned a bit earlier. Okay, so as I was mentioning a bit earlier, multi-core is the thing that everybody's using as an excuse or a reason to kind of look into these things. I do believe that in addition to the slight faddishness thing that I was talking about a little bit earlier, what we are doing also is we are starting to go and recognize that that we can go and gain a lot of leverage by going and using more powerful abstractions in our program. And this is a slow thing which is kind of happening over the course of the industry. How many people here worked in Ruby at all? Some of you? I know there's a lot of .NET people here. The thing that's really kind of funny about Ruby, and really kind of struck me when I first started going and getting involved in the community, was that they were doing all sorts of crazy things with metaprogramming and stuff like that we were warned about back in the 1990s. It's like people were saying, oh yeah, you can use reflection to go and change things at runtime and all this other stuff, but it's really, really bad because you can screw things up terribly, so we're going to organize our language so that you can't possibly do such things, right? And of course, when you do something like that, then naturally people don't have a particular tool available to them, and they find crazy workarounds, right? What the Ruby community has discovered over the past 10 years or so is that essentially you can give people the full power of a language, and they can act responsibly. Not everybody's going to act responsibly, but the thing is, limiting the power that you give to programmers in order to go and sort of, just because you're scared what they're going to do with it, isn't really a winning strategy. At the core of it too, though, functional programming languages are extremely powerful. Okay, they give you a great deal of abstraction capability, and they do force you to think about things in different ways. So I think the feeling in the industry right now is that we are right to be able to go and use some of these functional variants to be able to go and sort of build things up from them. And we should be able to go and apply this in particular problem domains. So, example of functional programming. Everybody's heard of MapReduce from Google, right? Okay, it's kind of funny. This is almost like functional programming writ large. Okay? Essentially, the idea within MapReduce is you go ahead and you take big problems, you break them down to smaller problems. You farm them out to different processors. You take all the intermediate results and you kind of fold them together in order to produce the output result that you care about. Okay? This gets right back to that whole multi-core thing, right? It's great we can take big problems and decompose them into smaller bits, okay? Have them run independently. Notice that each of the small problems we want to go and take and farm out to a different processor, it can't really depend all that much upon things that are going on with other processors. It has to be an independent thing. not producing side effects. Okay? All the results that come back happen to be merged together, reduced into a single result. Okay? This is kind of like the core of functional programming in a sense, and this is a case where people are adopting something like functional programming in order to solve big problems using multiple processors. Right? It's funny when MapReduce first started being popularized and talked about within the industry. A lot of functional programmers looked at it and said, "Oh God, you're just talking about map and fold. That's just these are two fundamental operations within any functional programming language." What they did is they distributed it across hardware. And it's like they gained a lot of power doing that. And it's like, yeah, that's great. They did that. This is by way of background also. Anybody know what this is? New syntax for lambdas in Java, right? If they actually get it done. They will at some point. Okay? They will have lambdas in Java. You will have closures. So you can go ahead and create blocks. Here's an expression. Okay, it accepts an int as an argument and evaluates to that. You can pass this thing into a function, okay, and then basically go ahead and have it be used. Here's a case where you have an expression and it goes and evaluates to a block, and it's just an anonymous function you can pass into something else. This is the core of functional programming, the ability to go pass functions to functions. And the terminology that's quite often used for this is higher order programming, higher order functions. So in Java, this is coming up. In God help us C++, okay, that's all one word. Okay, we now have lambdas also, and they're coming in the latest standard. You might look at this and say, "Gee whiz, what the heck's going on here?" But this is a lambda. Okay, this is a function, and it has this little specifier here, which goes and tells us how we're going to interpret these arguments. If you don't read C++, what's going on here is we have this algorithm called for each, okay, that we can go and apply to a vector. And we can go and take the beginning and the ending of it and pass this function to it and have this thing be applied to what we have there. Now, being C++, they chose to and give you all sorts of options in the way that you, when you create these lambdas, the way that you're able to go and sort of access variables in the outer scope and stuff along these lines. And that's what we're seeing right here within the specifier list. For those of you who want to go and dig into it deeper, this is essentially the syntax you use for specifier lists in C++. I'm going to go on the slide more than 5 seconds, so memorize it quickly. No, they basically give you all these options in terms of how you can basically treat these functions and pass them into other functions. So yeah, C++ is moving in this direction. Okay, kind of bizarre that we have that, and you do have lambdas in C#, right? You do have blocks in Ruby, right? All the elements of functional programming are starting to get there. The key thing we want to recognize about object orientation and functional programming, I think, is that they really have the same goal. Okay? And it took a while to kind of see this. Okay? Even though they appear to be very different paradigms, the goal is to be able to go make programs more understandable. Okay? So how does OO do this? Okay? The way object orientation basically attempts to help us with understandability is to go and basically make things local, to go and guard the local area that you're looking at in your program. We know that as human beings, we only have a certain amount of detail that we can handle at once, right? And so if you're looking at a big procedural program and you have 15 global variables or 100 global variables, right? And all sorts of nested state craziness, it's really hard to want to look at a couple of lines of code and see what's really happening. The cognitive benefit that we get from object orientation is that we are able to go and create these little packets where we basically care only about what's happening inside and what comes at us from the public functions. And when we care about those things, then we can go ahead and sort of, see a local context, understand it well enough so that we can go and figure out how that local context will interact with other contexts, other objects. In functional programming, the idea is a little bit different. It tries to gain understanding via immutability. Okay? Now this is kind of weird. Why would immutability aid understanding?
No side effects.
Yeah, no side effects, right? It's that thing I was talking about with legacy code a while back, that you are going in there and you're poking at something and you have no idea what's going to change as a result of the thing that you're doing, right? If things never change, then you don't have any side effects. But I'm sure that this seems like voodoo to you if you haven't done a little functional programming. How can you possibly do anything realistic when you don't have changing data at all, right? What it turns out to be, though, is that when you're working functional programming, you tend to have immutable data structures that simply can't change, but then there's basically, you deal with them in a very transformational way. Okay, so for instance, if I have some kind of a set abstraction, for instance, I might have a function called add. And I pass in a set, and I pass in the thing I want to add to the set, right? So just using some pseudocode here. And in the process of doing this, what happens is I'm not modifying this set. I'm producing an entirely new set. Does it seem really inefficient? How big could that set possibly be? Right? Just think of the sets you've ever dealt with, hundreds of thousands of elements, stuff like that. Seems really inefficient, doesn't it? Turns out that in the functional programming community, what people have done is they've done an awful lot of work to go and basically optimize these operations so that they really are fast in spite of appearing to be slow. Okay? To give you a little skinny on this, what happens behind the scenes is if you have a set and it's organized like a tree, right? It has all these tree elements and stuff like this. What happens is that if you choose to add an element, and it's going to be down here at this node, for instance, what happens is that a new set is created. Basically, it has a copy of this root element. Okay? It points to all the things that aren't changed. And then it has its own copy of this piece here, and then it goes ahead and adds the piece to it. That's going to be the new piece. So when you pass this thing back, look at how the node structure is. Okay? Essentially, this thing is still pointing to the other things that are there, plus a path to the new element. Right? So this is actually sharing part of the tree. Okay? And you get back this set, and when you iterate through it, you basically see all the elements you had there previously. Right? None of them are changing at all. But it ends up being the case that you aren't really going and taking the entire damn set and copying the whole thing over. Right? So there's all sorts of little tricks that happen implementation-wise like this that make, they allow us to go and have in functional programming this illusion that basically we are going and making a complete new copy of something. But when we're able to do this, actually things are far more efficient than expected. Now, the reason that immutability is really kind of useful for us is that it does really allow us a great deal of reasoning ability. Okay? There's a great deal of, we were talking about locality in conjunction with object-oriented programming a few minutes ago. But the cool thing with this is that essentially it's like when we do this, we know that this is never going to change. It's very easy for us to go and basically sort of see in this particular local context, it's like, we just have the stuff going in, the stuff coming out, and I don't have to worry about changing things in particular ways. And it's just really a very handy way of working with things. Unfortunately, though, it is a very counterintuitive way of going and looking at the world. And it takes a bit of effort to go and sort of arrive at a good working knowledge of design when you're working this particular way. It does seem very different from what we're used to in object orientation, though, right? Or does anybody feel like it's the same damn thing? No? Okay, it's not. Right. So I want to go and basically approach this from first principles. This is going to be a very odd part of this presentation. But I think it's kind of powerful when we start to think about where functional programming belongs in our systems and where object-oriented programming belongs in our systems. Anybody know where the root of object orientation comes from? Where does it come from? Well, if you know, you got one up on me because it really has multiple roots. Object orientation came from a couple of different avenues within the history of computer science. There was Ole John Dahl and Kristen Nygaard working on Simula back in Norway. And what they were doing is they were trying to go and find a way of extending abstract data types within procedural languages so that they could go and do simulation work. And then they started saying, okay, well, look, we can have these things which are concepts of things in the world, and we can go and have procedures associated with the data. That would be a really cool thing for us to be able to do. And that lineage ended up spawning C++ and other things like this. Another avenue that really kind of started up back in the 1970s for object-oriented programming was Smalltalk, right? And Alan Kay, basically came up with some of the original ideas behind Smalltalk. It was behind the research impetus to go and basically create Smalltalk. And when he talks about object-oriented programming, he says, look, this is the metaphor. Okay? In object orientation, because he has a bit of a biology background, in object orientation, it's not the objects that are important, it's the messages that we send between objects that are important, right? Somebody ever heard this terminology that it's all message passing in object orientation? Yeah, it's a very old idea, and it's one of those things that you typically don't see in the C-derived languages like Java and C#. You see this dot function, and it's easy to believe that you're calling that function. When in essence, what you're doing is you're sending a message to an object, and depending upon what class that object is, that tells you which function is actually going to be called through virtual dispatch. Right? The notion that Alan Kay had was that essentially, we know that nature scales pretty well. So why don't we basically go ahead and say, look, we can organize systems as these little independent pieces, and they basically solve problems by sending messages back and forth between each other. okay? What's the messaging mechanism for cells? Anybody know?
Synapses?
Well, that's in the brain, yeah. Yeah, they are cells and everything like that. But generally what happens is it's chemical messaging, right? It's kind of like a cell will basically emit a particular chemical and it basically goes and feeds through the membrane of another one, and then the cell reacts and then goes send other chemical messages to other cells. From what I understand, I'm not a biologist, I don't even play one on TV, right? So that's the way I understand biology, okay? But the thing is, it's a very cool metaphor when you think about it. What's neat about it, though, is that we can kind of carry things a little bit further. Why does this end up working very well in the body, in organisms? You know, why is it the case that we can go and have cells die and new ones come in and not have decoupling between them and stuff like that? You know, what it turns out to be is that essentially, in object orientation, it's all message passing. What we get from this is basically pure, it enables asynchrony. Okay? We can have asynchronous messaging with this model. Okay? To go and give you more of a flavor for this, take a look at this. Okay? If we have this function here, and we send a message called go to the other object. Okay? What's our responsibility right here after we've done that? That's a very big question. What is our responsibility after going and sending this message? Wait for it.
Wait for a response?
Well, to wait for it. The thing is, because in most computing environments these days, we do have a synchronous model. We're going to wait for that message to get sent before we start executing this other code. But what kind of code can we have here? We can basically do anything we want to, right? And the thing is, once we've completed the function call, or the method here, then basically we're returning control back to the higher level, and then somebody can go and call us again, right? They can want to send another message to us, okay? But the synchrony is something that we basically have baked into our systems because we are doing generally single processor stuff, and that's just been the model going forward in computer science. Now, what about this over here? Suppose that I go and do this, okay? I tell this other object to go, but I get some kind of result back. What kind of things can I do here? Well, there ought to be a reason I'm getting a result back, right? So if I am getting a result back, perhaps I'm going to check it. Perhaps I'm going to go and actually make a decision based upon the result that I get back. And in a way, what that happens with this, that ends up going and coupling us to this other object, okay? We are not just going and saying fire and forget, go ahead and do things. What we're saying is, look, we're going to wait here until you're done. You give us something back, and then basically pretty much obliged to do something with it, right? So it's an interesting thing about this. Asynchrony is really the ultimate in decoupling, okay? You basically just sort of fire off things and you don't care, okay? Basically you just sort of wait there, you want to have other things talk to you, and then go on with that. Has anybody ever heard the saying that good object orientation is tell, don't ask? You heard this at all? It's a little amendment inside that pragmatic programming book by Andy Hunt and Dave Thomas. They say that in general, good object orientation happens when you tell objects to do things. And then basically they go ahead and they do those things, but you don't really ask objects questions all that much. If you ask questions, then you often get into the situation where you're like, okay, hey, give me an answer, and then I go and I fiddle with it right here, and I go and I take it and I go and I pass the results over to this other object and stuff like that, and you end up being a middleman, and then ends up introducing a lot more coupling than you would have otherwise. Okay? So good object orientation tends to be this way. The message passing metaphor is great. What it allows us to have is asynchrony. Okay? Radical decoupling. Now, the thing about functional programming, the thing which makes this kind of interesting is that in a way, functional programming is a way of abstracting away time in many cases. Okay? This is going to sound kind of weird, but there are many styles of functional programming where, you aren't going and saying this program is going to go and proceed this step by this step by this step by this step by this step. Instead, what you do is you say, look, I want to go and create a list of things, okay? And I'll pick out the one that's like the 15th element of the list. And that 15th element is kind of like the same as going and iterating through a loop 15 times. It may sound kind of counterintuitive. I'll show you an example of this a bit later. But there is this notion in functional programming that what we're doing is that in many cases, time is like a list to us, right? What we allow ourselves to do is kind of unfold computations into structures which allow us to go and pretend that time doesn't happen in our programs. I know that sounds weird, but let's carry on, and I'll explain more as we go forward. Anybody know what that is at all?
Mandelbrot set.
Yeah, this is actually the Mandelbrot set. And unfortunately, Benoit Mandelbrot died like, what, a couple weeks ago, I guess? Poor guy. But he, he basically came up with some foundational ideas behind fractals. And, made everything kind of richer. When I was much younger, I had a lot of fun going and writing code to go and create Mandelbrot sets. And back in those days, it was really arduous because you have to calculate the value of each pixel, okay? And every pixel has an iterative process associated with it in order to determine what color it's going to be. And in the early days of computing, the time that it took to go and do this sort of thing was just rather onerous for PCs and such. It's an interesting thing you can do with functional programming in order to go and sort of solve this problem. Go back to this slide. Okay. This is the type of thing that you would have if you try to do this in an imperative fashion. You go and say, look, there's a particular square for the Mandelbrot set that I want to go and evaluate. Right? I want to go and actually go ahead and produce a picture for this. So you basically have two nested loops. You're going to iterate over x, you're going to iterate over y, and then for every single pixel that you have, you're going to basically iterate over certain values until you get to the point where you basically determine what the color is going to be. So we can kind of imagine that those are the three loops that we have when we're doing this sort of thing. Right? When you're working in functional programming, you can do something very different. Okay? I'm going to show you this and explain it, even though it's utterly bizarre. This is Haskell, okay, Haskell programming language. I'm not going to go deep into it because the syntax is pretty damn bizarre. Okay? What this thing does, though, is it defines a function called Mandelbrot. And you give it a point, and you give it a double, and it produces a list of lists. Okay? Now, the point is basically the point at which you want to go and basically start, like the upper left point, for an area of Mandelbrot system. And the double is basically how far out you want to go for the next point. Okay, so it's kind of like the interval that we're going to go after this whole thing. What this function does, though, is it actually goes and produces an infinite list, an infinite grid, starting at a point going out leftward and down. Okay? So you have this infinite grid, and you might look at this and say, okay, well, infinity sucks, right? I mean, the thing that's terrible about infinity is you never get an answer back, right? So what's the point of this? What's neat about this, though, is it enables a different style of programming, okay? Where basically we can go ahead and kind of impose edges later on what we're doing. So let me show you a little bit of this to go and give you a preparation to go and see what's going on with this. This right here is some Haskell syntax, which basically allows us to go and sort of take some sequence that we have and take the very first 5 elements and return them back to us. So it's kind of transparent what this does, right? You have a sequence from 1 to 10. We take the first 5 elements and we get them back, right? Now, what about this right here? That actually does the same thing, okay? Except this thing right here is an infinite sequence from 1 to infinity, okay? If you were to the Haskell interpreter and you actually just typed in this and told it to evaluate, what it would do is basically just start printing 1, 2, 3, 4, 5, and we'll just keep on going on forever, just printing out numbers. Because this expression right here generates an infinite sequence. Now, the cool thing about this, though, is that we don't have to worry that in evaluating this particular thing, we're going to evaluate everything up to infinity. Because the way that this language works is that basically you get things only on demand, right? You basically say, look, I'm going to go and take the first 5 elements. Let me go ahead and take the first one, second, third, fourth, fifth, I'm done, right? And when it goes and asks for those elements, it basically goes to the sequence and says, oh, give me your first one, your second one, your third one, whatever. Oh, you can compute what many more? I don't care about that. I just want the first 5 elements. This is called lazy evaluation. It's an extremely powerful way of going and working. It enables different forms of abstraction. So we have something like this, okay, just to kind of underscore the point. This right here is a generator expression, a list comprehension, where what we're doing inside this right here is we're saying, look, we want to go and generate an infinite list of squares, okay? We're going to take all the values from 0 to infinity, and one by one, we're going to multiply them by themselves and produce a new list from it. But we just want to go and take the first 5 of them, okay? To underscore the point even more, I can actually go ahead and take this expression and assign it to a variable, okay? And then say take 5 of squares, and I get the same result. In a way, it's kind of like saying, look, we have these things that look like data, these infinite sequences, but in essence, what they really are is that they are these functions, right? You basically evaluate these functions by saying, give me the next element, give me the next element, give me the next element. It's kind of like iterators in C#, okay, in a way, the way that lazy evaluation works. Now, let me ask you a question about this, though. What does it take for language to have lazy evaluation? What would happen if we omitted side effects in our expressions? That would be kind of weird. Suppose that inside of here, I had some expression just floating around in here, and you can say, look, you know, on the 7th element, what I'm going to do is I'm going to update a global variable over here. Every 7th element, I'm going to update a global variable. Okay, what would that do to this program? Make it pretty hard to understand what the hell is going on, right? Because the thing is, when you have this expression, it's really going to be the context where it's used that's going to determine how far you go in generating that sequence. Sometimes you may go to the 7th element, sometimes you may not. And you're just going to have this kind of hidden information stuck away there, and kind of side effects which occur at random points all the way through your program. And that's the thing which is kind of interesting about all this, is that essentially laziness, okay, this lazy evaluation thing, is something which is really enabled by not having side effects. It's enabled by having immutability, okay? Let me jump back to that Mandelbrot set example that I gave you a bit earlier. Okay, that's the Mandelbrot set function. Okay, it goes and takes a point in a double and produces a list of lists. There's the way you can actually work with this is you can use functions like this, range. Okay, what this thing does is basically says, look, I want to go and I'm going to drop the first m elements from the sequence. Then I'm going to go and take n minus m elements. So I'm getting like a little chunk, a little subsequence of a big sequence. And I want to go ahead and take those particular pieces and use them. What you can do with this is you can say, look, I have a function which goes and computes the infinite Mandelbrot set. And what I want to do is I want to go and basically take a range function and go and basically find just one little slice inside of it. Okay? So it's kind of like saying, look, we have an arbitrary computation and we can impose the edges later in order to get the thing that we care about. It can all be like queries in a sense. This does enable a lot of very interesting abstraction going forward in programming. I'm sure you know that your life is really painful when you're working with edge cases. Right? If you have edge cases in your code, it gets kind of crazy. Many things become much simpler when you can form a general computation and kind of impose the edges later. Okay? That's a neat thing that you have possible for you within functional programming. So anyway, there's two different aspects to this, as I was pointing out. Essentially, with object orientation, if you carry it to the extreme, you get radical decoupling and it enables asynchrony. Okay? With functional programming, if you carry it to the extreme, you're using immutability all over the place and it enables lazy evaluation. Right? So, two different things. How do we mix them? This is the hardest part of this. Okay? As I mentioned a little earlier, object orientation that is good generally is tell it on DAS. In functional programming, you're never going and saying, hey, change the state of something. You're just asking questions. Give me this, give me this, give me this, give me this. All right? How do we make these decisions normally when we're going to program? How do you choose between having getters and commands that go and send to some object? It's a really abstract question, isn't it? How do you decide between a push and a pull architecture? And that's really a kind of interesting thing. We know that we can simulate push with pull and simulate pull with push in architecture and stuff like that. But making a choice about which to use in which particular place is kind of interesting, kind of odd. One thing I've kind of noticed is that it seems like it's far more natural to go and say, look, if we're going to have an architecture, it's better off that we put the objects on the top and functional programming bits on the bottom. Why did that make sense? Is there any reason why that would make sense? Well, consider the inverse. What if you put the functional programming stuff on top and YOLO stuff on the bottom?
Well, then you got mutable stuff on the bottom, but you're trying to encapsulate it with immutable.
Yeah. And that's kind of funky. I mean, it seems like it's more natural to go and say, look, let's use object orientation for general decoupling, okay, the top level, and use functional programming for a lot of our calculation bits down underneath, right, and get the best of both worlds doing that. Now, I sat on this idea for a long period of time because I thought, okay, well, when we go and discuss this someplace and stuff like that, everybody's going to go and point out a year later that that's a radical simplification and it doesn't make much sense. Right? In many cases, there are so many counterexamples of reasons why you wouldn't want to necessarily do this. Let me show you one. Jump to, Well, okay, just one thing I'll mention. You know, anybody use link at all? Okay, you use link? Okay, that's great. What does link operate on? Objects, right? But what it does is it allows you to go and do these things like, okay, I want to take a certain number of things, skip a certain number of things. You form these functional expressions based upon these objects. The thing that's kind of cool about that, though, is that even though those are objects underneath and they can be mutable, the operations themselves aren't really mutating, right? That's generally true, isn't it? So that kind of points to a way that we can have layering of object orientation and functional programming inside the system. It comes down to this key idea here. Has anybody ever heard of this before? Referential transparency? Okay. If you look through functional programming books, you'll see this term bandied about quite often. It has a very particular meaning. It basically means that if you have some function, okay, inside of a system, let's say I have a function called inker, and it takes x and it produces x plus 1, then every place inside my program where I say like, inker of 7 plus inker of 8, I should be able to go and substitute the arguments for this. And it should be like 7 plus 1 plus 8 plus 1. Just replace the body of that particular function application inside an expression and they get the proper result. Okay? Referential transparency means I can replace the text of that thing every place where the call happens. And in functional programming, we call all these things calls. They're just basically expressions. The cool thing about this, then, is that it's easy to go and reason about all these things when you have referential transparency, right? You can basically know when you look at a particular piece of code that, well, look, it's just every place that I go in and do this, I know that I can replace it with this, and I just understand what's going on with things. So referential transparency, what gives us that? Well, that mutability stuff is kind of cool, right? If you have things that are mutable, then you're not able to change states, so you can get referential transparency. Okay? If we didn't have mutability, we could do something weird like this. We could have our function and have it increment like y, where y is a global variable here. And whenever we call this, it's going to go ahead and increment this variable, and it's going to replace the text here with these things, and then producing side effects and making our whole program go kind of haywire. So immutability kind of aids referential transparency, but the key thing to point out, though, is that you don't need to have complete immutability in order to go and get referential transparency. So let me give you another cool example. This should have made that bigger. Can you kind of see what that is? Everybody squint? Okay. It's a simple function. It basically goes through an array of fields in Java. Okay. And what it does is it goes and takes the length of every one of those fields, adds it to a result, and returns the result back. Okay? Does this have any side effects? Well, kind of a hard question unless you look down and see what's really happening in get bytes. We kind of hope that get bytes doesn't have any side effects, right? Okay. With this particular function right here, we do have mutable data. We have an integer that we're basically going ahead and bumping up every time by the number of things that we have, right? So we don't have purely immutable data within here. But the thing that's cool is that we don't have any side effects. So we can technically go ahead and basically take this and substitute the code that we have here for every call we have to get body size and have an equivalent program. And that's referential transparency. So it turns out that there's some forms of state mutation which don't give us trouble. Okay? They don't give us trouble when we are working in a particular functional style in a way. But when you kind of carry it back to what we were talking about a little bit earlier, essentially, if you're looking at how you want to mix functional programming and object orientation, it's okay to have objects underneath as long as you aren't, through the functional layer you're working in, changing them. Okay? And that's what makes link work okay, right? It's all about queries and going to bring back these objects, but you really hope that these expressions aren't going to be changing the objects as you do that work. If they are, then you're not going to be able to look at that expression and really reason about what it's really doing for you. Does this seem similar to anything anybody else has ever seen at all in programming? There's something weird here. Y'all know the term parametric polymorphism? Okay. So the $2 word for this is generics, right? A real simple word. Okay, when you have generics in Java and you have generics in C#, these are basically mechanisms for getting this particular style of polymorphism, parametric polymorphism. And with parametric polymorphism, what you're doing is you're parameterizing one type by another. Okay? And it seems, what you end up having is essentially this notion that we can define all the operations for this particular thing in an array list. And we don't have to know what the type of this thing happens to be in order to basically make this particular thing. Does it matter when we construct an array list what kind of X we put there? Not really, right? It could be an account, it could be a car, it could be a map, it could be anything, right? But we know that we have code within an array list that's going to basically make this thing work all correctly. It doesn't make any real assumptions upon what's going on with this particular bit. Okay? In a lot of functional programming, you end up having the same style of thing, right? You basically have things which operate on other things, so they operate on collections of other things, rather than operating on the things themselves. So it's kind of like if you have like a big link expression that's working against objects, they may be mutable. You don't want to go and mutate them within the context of this thing because this thing is really like a wrapper. It allows you to perform operations on the collection of these things rather than the things themselves. So that's a place where layering can happen, where you're mixing object orientation and functional programming. I know what that is? It's not all of it, okay? Whenever new technology comes out, people start to abuse it for very strange reasons. This is actually a very small part of a page-long ray tracer written in link expressions. Okay? Imagine creating a ray tracer in link expressions. It's not the sort of thing you really expect people to do in a typical program, but being a consultant, you look at something like this and you say, okay, that's what we're looking at a year from now. Everybody's going to go link crazy in .NET. They're going to go and do crazy things with the link syntax. So yeah, essentially link is a full functional programming language in a sense. It's all about querying things. But you can work in this way where you don't really have side effects and produce like a big rendering of something, and at the end of it go and iterate through and basically set all the pixels based on the rendering you have. It all gets lazily evaluated for every step you go through. It goes and calculates the pieces that it needs and goes and marches forward. It is functional programming embedded within C# and rather powerful. So we can go and mix these two things that way as long as we're conscious of the fact we don't want to change things in the substrate. And so that's essentially what I've been saying with this. Okay, design. Never hear of this at all, expression problem. Okay, well, the goal is to define a data type by cases. In one hand, new cases of data type, new functions over the data type that we combine in existing code. Okay. Does this sound familiar to anybody? Like you've seen something else in object orientation that's similar to that? You ever hear of this one at all? The open-close principle? Yeah. What is the open-close principle? This was first articulated by a guy named Bertrand Meyer a long time ago. He developed a programming language called Eiffel, and he basically came up with a lot of the core things we know to be good in object orientation these days, the articulated principles for these things. And his notion was that in good design, what we're able to do is we're able to go and create these abstractions that we don't have to modify all that often. We can add to our program by adding new abstractions. Okay? You can subclass existing classes rather than going and modifying existing classes. That was the idea that we had with this particular thing. And one of these things that you'll see over and over and over again as you're programming is that some programs accommodate change better than other programs do. Okay? Typically in places where you have programs that have like very long methods and very big classes, you have lots and lots of changing these things over and over and over again. Anybody know why that happens? Single responsibility principle, you ever hear that? It's the notion that a class or a function should have a single core focused responsibility. And if it's all about this one thing, doing just this one little thing, chances of you going in there and having to add something to it are kind of slim. You just create another thing which does another one little thing. And you can post those things together. And that's really a foundational thing in object-oriented programming. Okay? It turns out that in the functional programming community, they've encountered this same thing, the open-close principle. They encountered it, though, by going and looking at how to go and create larger functional programs. They termed it the expression problem. How can you go about going and adding to an existing data type without going and modifying the source? Okay? It seems like a very strange thing to do. Let's take a look at the little problem here. Suppose that we're working on, suppose that we want to create a new operating system. We're going to use an object-oriented language to do it. Okay, that seems kind of like a strange thing to consider doing. But if we're going to create like a file system for an operating system, we've got to arrive at what our abstractions are. We might have the notion of a node. right? And you might say, well, what is a node? Well, at the very least, a node can be something like a file. And you can also have directories. Nodes also. And you can also have links in your file system, right? And you probably have a bunch of other things also, right? Seems reasonable, okay? What kind of operations should a node support in a file system? I want to call any out?
Delete.
Delete, yeah, should be able to go delete, remove, or something like that. So we have delete here on node, and we have on all these things, right? What about copy? Should be able to copy links and copy directories. The logic will be different for doing those things than copying for files, okay? We can put copy in there. What's copy going to accept as arguments? idioms for functional programming will make things much clearer than they would be if you're using objects. It's kind of funny.
Source and destination.
Yeah, source and destination, although since we're on an object, we always say that we are the destination or something like that. We can say we are the source. We have to go and figure out how we want to sort that particular thing, right? How many possible operations can you have on file nodes and directory nodes and links and stuff like that in an operating system? Is there any bound to the number of operations you can have? Yeah, it's just insane. You can add more and more operations over and over and over again. And we do have this very strange situation going on here that over time, what we're going to have to do is add more virtual functions over here, more abstract methods, and then going to provide implementations for every single one of these things. And we're going to end up going and sort of being this odd situation where we're going to end up modifying a lot of code all the way through in order to go and do these sorts of things. Okay? So it seems like we've got a bit of a maintenance problem. Does anybody know what the typical OO way to go and deal with this thing happens to be?
You have some sort of service that manages the objects.
Yeah, you can have something which encapsulates that sort of thing also. But there's this pattern which is kind of obscure, and we're kind of lucky that people don't use it too often because it's painful. But there's the visitor pattern. You hear the visitor pattern at all? What you can do is you can create some abstraction. You call it a node visitor, right? And when you have a node visitor, what happens is you're able to go and say, look, let's go and have a bunch of different things here. Like you can have copy as one operation. And we can go and have like delete, all these other operations. And what happens is we set things up so that a node accepts a visitor, and it's able to go and traverse the node structure and say, okay, well look, it's like I have a copy operation that's, there's a copy operation that I have which is sufficient for files, another copy that I have which is sufficient for directories, and one is sufficient for links. And you have all those operations on this particular thing. What you're doing is you're kind of moving the work that you need to do in order to go and add an operation into this other hierarchy, okay? So you don't have to touch all these things over and over and over again. What you do is you create a new instance of node visitor for the type of operation you want, and you have to have a function for every single one of the different types that you have here on the left-hand side. So it's kind of like taking the locus of change and moving it over into another area, okay? So this is kind of like an object-oriented solution to the expression problem. What's going on with this is that you're trying to basically minimize change in a particular area and sort of still be able to accommodate change. Now, it's kind of funny, when you're working with functional programming, they kind of arrive at a different way of doing things. This is some stuff from Scala. Okay, you've heard of the Scala programming language at all? Okay. OO functional hybrid. Okay. They have something there called case classes. What case classes are is kind of like having a class, okay, which allows you to perform like a type-safe switch statement on it in order to determine what you want to have happen to the particular bits of it based on what you've got. So we have this abstract class here called term. This is for like a little language. We have a case class called var, one called fun, and one called app. And what happens is that once you use this syntax here, you can create instances of these particular classes by going in and using the name of the class and passing as arguments the things that they need. So here, what we're doing is we're creating a fun, which basically accepts as first argument a string, and accepts a body, which is a term. We've seen that all these things are terms, right? In this case, the fun is accepting another fun. So the fun is basically defined in here like this. We can build up arbitrary expressions using all these pieces. Okay? Seems kind of okay? So here's the thing that happens in functional programming, which is a bit different than what you're used to in object orientation. What you can do is you can create particular functions that go ahead and deconstruct the cases. That's what this is called. What you do is you basically do case matching for these things. So we have this function here called print term, accepts a term, and what we do is we basically choose to go and match on the term. If it's a var, okay, then we're able to go and get the n out of it and print it. If it's a fun, we can go and get the name out of it, which is x, and the body, and we can go and print out, we can print out the name using a caret in front of it and a dot, and then print the term. Okay, that's this. And what is print term here? Well, it's a recursive call to this. Okay. So what goes on with this in functional programming is it's kind of like since you have these immutable data structures, and you can't change these case classes after you produce them. What you're able to do is sort of pattern match on the particular components of these things, and then do this work in order to go and start to piece things together. I can create arbitrary functions to iterate through the structure of a term expression and do the things I want to go and do with it. Okay? Does this freak people out in object orientation? Magnus? Yeah, can you explain?
Well, it's like 2 times syntax in C#.
Yeah, I was really looking more like the case expressions themselves, and that what freaks me out about this when I look at this is kind of like, from the time I first started object orientation, people say, oh, switch statements, they're bad. Don't do switch statements. Usually means that you have an opportunity for polymorphism and you're not really using it, right? But the thing is, pattern matching is something which is kind of part and parcel of most modern functional programming languages. The thing that's a little bit dangerous in a sense, or kind of awkward with this particular thing, is that all these functions that go and operate on the different cases that you have for this data structure, it's kind of like you don't want to have some of these functions over here and some of them way over there. Because whenever you change your data structure, you're going to change these functions and then change these other functions over there, right? It's a typical open-closed violation we tend to have in object-oriented programming. If you have like a shape hierarchy, right, and you basically have circles and squares and ellipses and stuff like that, and you have a switch statement someplace saying, oh, are you a circle? Okay, draw you this way. Are you a rectangle? Draw you this way, whatever. The more you have those things scattered across your program, the more you can get into these crazy areas where it's kind of like, you have to go and do this big maintenance change whenever you choose to go and change the internal data structure. So it's kind of funny, in functional programming, you end up having this sort of thing. And it's a little bit counterintuitive to what we're used to in object orientation. But the thing is, it's not all that bad, really. If you keep the functions together, which tend to operate on the cases of data structure, then it acts kind of like an object does, in a way. And so that's kind of handy for us. We'll skip that and go back in a minute. Somebody ever seen code like this at all? It's kind of weird. This is for DSL. Okay, this is part of Handcrest. Have you ever heard of this at all? I realize now most of people are really more in the .NET community, right? Is that true? Okay, so Handcrest is this library that's kind of factored out of a mocking framework called JMock in Java. And what they have here is basically this style of programming which enables the DSL style of programming that we're very used to within the context of our work. So in the DSL style of programming, what we tend to do is we tend to go and say something like, okay, I'm going to have this particular object, and I go to it and I get another thing, another thing, another thing, and I call it and I do various things. And you're able to write things out in an English sentence in a sense. So you can say something like, 3 dot is equal to, just sort of in a very English style, go and do the things that we want to do. But typically what happens is you go to an object and you make a call passing other objects into it, and you get back another object that you can reference, right? Sometimes people call this the fluent interface style of programming. It's becoming more pervasive in the .NET community also, okay? This is a very functional style of programming, okay? And it's very close to the kind of things that people do when they're structuring functional programs. So to give you another example of this, one thing I was working on a while back, just for fun. I know you're not going to read this, I'm sorry. I was working on this little toy problem of going and creating like a list box model. Okay, you have like list boxes and desktops and stuff like that. A model for going and creating list boxes. And it's really kind of funny to think about how you would actually do this sort of thing when you don't have mutable state. Okay? How does a list box operate? Okay? When you have a list box, okay, you have a certain number of elements in the list box. You have one particular one which is like your selection. Sometimes you have a selection. And what's kind of funny is that maybe in this list box you have 102 elements, but you're really only showing like the first 10. Okay? If this is the selected element and we choose to go and arrow down, what happens? We move the selection. We arrow down again, what happens? We move the selection. If we're down here and we arrow down, what happens?
Let's move on.
And we're going to scroll. Right? So how do you model that when you don't have any mutable state? That's really kind of a funny question. What I arrived at with this particular thing is to go and say, look, rather than storing a list of all the elements, what I'm going to do is I'm going to go and having a window and stuff like that. I'm going to set up this structure where I have an arbitrary list that I pass in, and I have this structure which allows me to say, look, I've got a window, and the window is going to be some maybe it's like 3 to 7, for instance. It's going to be 3 to 7 within this particular list box. I have a selection. I'll say element 4 is my selection. And this data structure is really the thing that goes and models the list box. 2 indices are going to tell me what the window is, and one they're talking about what the selection is. So all of my operations can be basically like, okay, I arrow down, I'm going to go and bump this up by 1, and if it goes and gets to 7, then I move this thing over, right? And so each time you're going and creating a new data structure, a copy. So you say arrow down, you pass in one of these things, and you get another one back, right? At the end, you can take this thing and apply it to a list, and get all the things that should be in the window, and figure out what the selection is, and do everything you want to within the system list. Like I said, you tend to think about things in a very different way when you're programming in a functional style. So I can't walk you through the code for this because it is kind of strange, very odd language. But the thing to show you here, it's kind of interesting, is this. Okay, this is the set of signatures for all the functions that I just wrote. Okay? The syntax for this in Haskell is kind of funky. What you have here is you basically have these arrow expressions, and what happens is that each of these is like a parameter to the function, except for the very last one. The very last one is the return type. Okay? So what we're saying with this is that we have a function called window at edge. It accepts a window, and it returns back a boolean. Selection at edge accepts a window, and returns back a boolean. What about this function over here, page down? Accepts a list box model, returns back a list box model. Right? What about this one right here, page width? Now, that requires a bit more explanation. What goes on with this one is we actually accept, we have these parentheses here, we accept a function that takes a list box model and returns a list box model, another function which accepts a list box model and returns a list box model, and we accept a list box model and we return back a list box model. Okay? So this is a higher order function. We have this function which accepts 2 functions and a list box model and returns back a list box model to us. Okay? So you can see we have all this sort of thing. Is there anything kind of odd about these type signatures in a way? The odd thing about these things is that we have a lot of ones which basically go ahead and take a base type and return back a copy of it, or return back something of the same type and modify it. And this is an interesting thing for you to know as you're moving forward and trying things in functional programming, is that you do have a direct analog in functional programming to working object orientation. Okay? We are used to going and saying, hey, object, let me go ahead and tell you to do something and you modify your state. Right? We're used to doing that. In functional programming, we say, hey, we've got an object. Let's make a copy of this object with the modified state. Right? So what you end up with is you end up having these libraries which contain lots of ways to sort of like pass in particular types and go and get things back to a base type. And then you can basically go ahead and use that base type to pass to other functions. And go and do things to them and get back another object of that base type. So there is this analog there. So it's kind of useful to know that when you're trying to go and bridge the gap between these things. From what I've seen in functional programming, one of the things that happens, and it's rather deep, is that people start to go and build up libraries to do these things. They call them combinatorial libraries. But in a way, it's just really, they're kind of like classes in object orientation. The key thing is you can start to go and piece together expressions much the same way as you would in a DSL, like in Java or in C#. Okay? So this becomes yet another thing that you can do when you're mixing functional programming and object orientation. You can start to, in the context of an object-oriented programming language, create these functions which sort of go and give you new data every single time, piece them together like DSLs, and you've got functional programming. You're doing that in the context of what you're working on. Got another little picture here that goes and shows, kind of what's going on with this. You have an arbitrary type A, okay? You might have some function which accepts a C and returns back an A to you. Accepts a B and returns back an A. This one accepts an A and a B and returns back an A to you. And the thing is, every time that you've got all these functions return A's back to you, you can take those A's and pass them yet again to other functions that accept A's. And just have this composability. You can take these things and piece them together in order to form bigger expressions and do the things that you want to do. Compositionality is a very, very strong part of all of this.
Is that accepting a function from A to B and then returning it?
I would say no right now. Okay? This is basically going and saying I'm accepting these 2 arguments, returning one of these things back. There is a funny thing about Haskell and in many functional programming languages. The reason they use this arrow syntax here is because implicitly underneath the covers, pretty much, no function in these languages accepts more than one argument.
Right.
Okay, so it's kind of like you have, when you say add of 2 and 3, what you're really saying is take 3 and pass it to the function add 2.
Yeah.
Okay, it's called it's called currying, and it's something which happens underneath all this stuff. But for the purpose of what we're looking at right here, don't even have to worry about that. What this means here is that we're just accepting two arguments and returning back an A. Adam, were you?
Yeah, just back to the copying of sets. I was just kind of wondering before we move on too far, is that a trait of all languages, current languages that are functional and to some degree like C#? Or will have that optimization or no?
I'm not sure, because it's really a very wide community, the number of languages which do this kind of thing. One functional language is becoming extremely popular now is Clojure on the JVM. And it's a Lisp derivative, and they basically they've done an awful lot of optimization underneath to make all that stuff work very quickly. And I think I heard someplace about Scala going and picking up their libraries to do this sort of thing. I really don't know what the situation on the in the CLR is for functional programming languages. I don't know quite how that works.
I just wanted to say, I wanted to ask that question earlier. I wasn't raising my hand to say that you're out of time.
Okay, I want to get back to it and make sure there wasn't some kind of an administrative thing. Okay, yeah. So anyway, I kind of thrown a whole bunch of things at you, and here I am, and now we're into it. And these were the things I wanted to talk about. And I didn't know quite what your level of expertise or knowledge about some of these things happen to be. But these are the conclusions I'm drawing temporarily right now about the hybridization of these things. And essentially, they really are very different paradigms. That when you kind of carry things forward from first principles, it does kind of make sense to have objects on top and functions on the bottom. And in fact, one thing I didn't mention in the earlier slides, which I think is really kind of an interesting thing, I really want to do more research into it to see how true it is. It seems to be true in many examples I see. When I look at many architectures, I tend to see that even though people aren't trying to apply this as a principle, it ends up happening. I mean, think of all the messaging architectures that you deal with, right? It's messaging on top, and then if you have getters, they really are down below in the code itself. If you look at some microcosms, like certain testing frameworks, like JU, for instance, it tends to have a very strong tell, don't ask style at the upper object level. But there are getter operations and stuff like that happen internally within this. I basically say to you, if you're kind of curious about it, take a look at the code that you're working on and kind of notice whether that tends to be a sort of like an unconscious architectural style, where you're doing tells at the top and asks at the bottom. So yeah, that's a conclusion of this, is that this is kind of a loose pattern. The other thing to point out is that you can layer this sort of pattern as long as you provide referential transparency in the areas that you're going to be using to work against objects. If you're going to do this functional stuff against these objects, it's kind of nice to set things up so that you really aren't mutating state. So you're able to go and give people reasoning guarantees of going and saying, oh, I see this expression, this, and this. I know nothing spooky is going on, so I can read this expression and see what's coming out of it, because it's not changing state underneath. The other thing, too, is that we've long thought in object orientation that favoring composition is good, okay, better than using inheritance and stuff like that. As we move more to the functional paradigm, composition becomes even more important and useful. It turns out that when you eliminate side effects from things, it becomes way, way, way easy to compose pieces together to go and do things. And that's kind of like a good thing for us. And I have to explain that. Favorite answers. It's all kind of tentative, but I just want to go and sort of share this stuff with you and get your reaction. Any questions, comments?
Yeah. I'm curious, I'm imagining that a lot of the same is starting to become available in Java, but in C#, the use of lambda syntax along with the action func, the full use of expressions as well. How much of that does that really provide in terms of being able to build as the type of architecture where you've got object-oriented style on the top and then internally you're leveraging functional programming?
I think it enables it a lot, and it's because it basically makes things compositional at the lower levels. I mean, it can be compositional at the upper levels too. But I hate to use this as an example because I know that only people here know Ruby. But it's like in Ruby, it's like you don't ever see a for loop. You just really don't. In Smalltalk, you don't ever see that also. What happens is you have these particular functions, and you say, look, okay, here's a function that's going to go iterate over the collection, pass in a function that's going to be applied to each element of the collection, right? And that's just the intrinsic way of working with things. And I think we're going to see that more and more in .NET. People really won't be looping as much as going and basically creating these lambdas and passing them into collections. And then we start to adopt this style, which really allows us to do some cool things. In Haskell, we have this really cool syntax where you can say, look, I have this function, dot this function, dot this function. And you apply this to some argument over here, and then the result of that gets applied to the next function, and the next function, and the next function. The function applies to it. We're able to go and chain things together in nice ways and compose them. When you have these pieces that allow you to do higher level things.
Is that similar to cheating?
Yeah. So it's, yeah, just being able to do that. Yeah.
In object orientation, we have a mechanism, the class, to group together methods and functions.
Yeah.
A way of organizing them. I'm wondering, in a typical functional programming language where you have these abilities and functions, is there a general paradigm for collecting together functions that have?
In a lot of languages, they're just called modules. You tend to, in most functional programming languages, have some notion of namespaces, which gives you some kind of well-defined scope of these particular things. Like F#, I think, has an export mechanism for modules, right? And the same thing is true in Pascal. That you're able to go sort of say, look, I have this file full of stuff, and there's only a couple of things I really want to export from this particular scope. The thing that's really kind of funny about this is that when you're really, you still have encapsulation concerns, right? But you're not encapsulating the state. What you're doing is you're kind of like hiding names so they don't start going and including other areas in your program. There is this notion that, you really want to encapsulate your types, kind of prevent your types from spreading too far along a program, because then it's like you get into this situation where, if the types are, you're betraying their data structures, then you change the data structure, then you get into, maintenance problems. So a lot of things are kind of analogous, but the things, the nomenclature that each language uses for these things is a bit different. And I think the conventions are a bit different than what they would be with classes. Yeah.
I understand that functional programming is just a completely different mindset. Where I have worked I've worked in a couple places over the last few years.
Yeah.
And there, for a large degree, a lot of developers are just really getting mature with OO now.
Yeah.
So is it really a value at this point to adopt a functional approach? Or maybe a better question is it a matter of functional maybe more difficult to learn? Do you suggest sort of a more advanced type of coders stick to that? Or I don't know if you even know if that's a dumb question or not.
No, it's not. I mean, I think it's a funny thing because I think there's never any like one adoption curve of the technology across the industry. The Clojure community is growing quite a bit in the JVM area.
Yeah.
The thing is, it's like you either have a problem where you feel you can get advantages from this or you don't. My feeling with this personally is that it took me a while to go and start to see things in these terms, functional programming, because I've been doing OO for so long, right?
Right.
So I kind of feel in a sense like some of this may end up just being generational in a sense, where if you learn some of the functional stuff very early on in your schooling and start to go and do the comparison and contrast, you basically have the mental toolkit to be able to go in and choose between them and adopt a worldview of each of them. It's kind of a tough change. I think there are benefits there. There are strong benefits, but it's really a question of maturity of the organization and how far you want to go. I think that's kind of answers for that.
Because I can say with a pretty high level of confidence, for me to go to my boss now and say, I think we should use Clojure for this, they tell me to take a
and that's fair. I mean, the thing is, you can always draw analogies to stuff which already exists. Like SQL is a query language and it's functional, right?
Yeah.
So people are doing this kind of stuff intrinsically in bits and pieces and stuff like that. I would never go to anybody and say you should go full bore functional right now.
Right.
I just think it's kind of ridiculous. I think it is something though that we should be aware of in our toolkits. We should, going forward, it's like experiment with a functional programming language, see what's useful, and of course, it's typical that you